Okay, so we are doing bonus 4, hand wavy derivation for what Q is. So Q, recall, is the shear force per unit length to glue two layers together. Okay, so per unit length, so we're going to ignore width in our derivation. So we're going to look at the beam sideways on. We're going to load it up, and I'm going to imagine that this thing's going to get squashed like this, and that at some height, which I'll take away from the neutral axis, we're going to examine how well this top bit of the beam is going to stick to the bottom bit of the beam. So sideways on, now looking from the end, sorry, not sideways, from the end. We've got the neutral axis, and we're looking at this location Y. And we want to know how well this top bit of the beam can stick to the bottom bit of the beam. It's worth noting from my previous description of Q that I'm expecting Q equals 0 at the top, because if we took this layer further and further and further closer to the edge, eventually I'm going to get a layer at the top which isn't trying to stick to anything, so there can't be any shear between the top and the outer surface. Right, what should I do? So I'm going to certainly I want the engineer's bending equation recasted into the vectorial form. So we've got stress equals my over I. Gonna want to use that, and let's look at our beam and examine a particular element. So we'll go sideways on for the moment. So imagine it's just deflected a tiny little bit. So it's pretty square. We've zoomed in quite a lot. So we're going to examine this little section here. So we're away from the neutral axis by Y. What can I say here? So we've got the I going through this section here, and going through this section here. So we've just looked at a little section from here, that's going to be delta x to that position there. I'm thinking I'm going to need the m is the integral of the shear force with respect to x, and probably I need to do another derivation for why that is the case, but we'll skip over that for now. So we put a request in if you want me to derive that. I can't recall off the top of my head. So here I can now differentiate that. So I can say that delta m over delta x is the v term. So when I move from here to here, it's pretty much going to stay the same. And I am looking for the force. Again, we're not too worried too much about the width of this beam. We're going to be working in per unit length. So I'm looking for the force that's acting, keeping the top section should have some colour pens, keeping the top section glued to the bottom section. So that's going to be my force there I'm looking for. So we've got a bending force behaving on this side here, and I know that I can use this formula here to find that bending force. And I've got another bending force on this side here. So what do I want to do next then? I want to look at integrating the bending force over this side and over this side. So if we were doing a 3D sort of projection here, so if we did worry about the thickness, what I want to do is integrate sigma on the left side and sigma on the right side, and I need a force. So this will, if I integrate this, will give me a force here, so force L, and integrate over this area, it'll give me force R, and the delta force is going to be my gluing force at the bottom. Okay, so what to do next? So the force at the bottom will be the shear force on the right integrated over its area. Take away the shear bending force on the left integrated over its area. So we've got the shear force right, take away shear force left, integrated over area. The I is going to stay the same. The y will be common for both of them, but there'll be a change in m. So when I substitute in my sigma my I, I'm going to take the I to be the same, assuming that when I'm moving from here to here, my I for the beam isn't changing. The y is the variable that I need to integrate around. So when I look at take the left, take away the right, I'm going to end up with change in m times y and integrate that. So that's when I'm going to now use this term here. So delta m over delta x equals v. So really I should have a derivation for this, but I don't. So that will become I v delta x y delta a. Okay, so how am I doing? Okay, had to have a little think about it. So what we're trying to do is get the shear force per unit length to glue these two layers together. So we're trying to get this force here per unit length. At the moment I've got the force along the bottom, so now let's divide through by delta x. So now I've got what I'm looking for, which is the Q. Whoops, that should be 1 over. Okay, so we've now got the whoopsie daisy. So we now got the derivation that we're looking for. We assume that V, the shear stress, we've seen previously that provided you're not at the middle where you flip over, V stays constant. So provided I take this to be a little bit away from the midpoint, I shouldn't have an issue. So that then gives me V over I, the integral of delta y over the area. And you can see now why we need to integrate from the y up to the top, so it's that total section. And then we just replace this bit here with the definition Q. Okay, so that's job done. That's all we have to do. Not a very formal proof, but it certainly does the job. So it explains to you where the terms come from. Okay.